Hello, everybody, and welcome to Lesson 0, our first lesson in our multivariable calculus course. So this video is going to be kind of a short overview about what kind of things you're going to see throughout the duration of this course. And we're going to kind of pick up where Calculus 3, where our introduction to multivariable calculus left off, but instead of going and dealing with derivatives, we are going to extend the concept from Calculus 2 of integration, but we're going to take it into 3D. So that's going to be the very first thing that we learn to do is how do you integrate in 3D? That's the very first thing that we are going to cover. And, just to kind of give some intuition, this will be covered a little bit more in depth in the next video, but in Calculus 2, we dealt with functions, with just two-dimensional functions, where x was our input, y was our output, and we talked about how to integrate for a particular range of x values, right? We did an integral from a to b of our function f of x dx, and what this did, what the integral represented, was basically it said, we're going to add up, right? Add up infinitely many tiny blanks. I'll leave blank here. And in this case, what were we adding up? Well, we were adding up a whole bunch of little tiny rectangles where the rectangle had a height of f of x and it had a width of dx. And we would say if you pick an x value here and you draw a little rectangle, right? We added up a bazillion of these. That's where the limit comes from. And we did it all the way for all the x values between a and b. And eventually that gave us area under the curve. So the integral itself is not area under the curve. This entire thing is area under the curve for this particular example. But from an application standpoint, one of the applications that we covered in Calculus 2 was, let's say f of x was, probability density, right? This is basically like the probability something happens, okay? And so we said, well, if f of x, if our function is basically the probability that some event occurs based on our input x. So maybe x is like your age, right? So maybe it's the probability that you win the lottery based on how old you are. Okay. Well, if you do an integral over that particular range of age values from a to b, that would give you the total probability, right? This integral would give you the total probability, of whatever event happening, whatever event that f of x is going to represent, the total probability of it happening for x going from a to b, right? For these particular age ranges here. And so we can very naturally extend this concept because, just like in the real world, the odds of you winning the lottery isn't just based on how old you are, right? It could be based on a variety of factors. It could be based on how much money you have in your bank account, right? If you don't have any money, you can't buy a lottery ticket in the first place. And so a natural extension into 3 dimensions would be to simply say that, what if we have a 3D function that is based not only on your age, right? It's not only based on your age, but what if it's based on your income? Okay, so now we have a 3D function. Maybe it looks like this. It's based on your age and your income, and it still represents the same thing. I still want my function here to represent the probability of something happening. Now that's not exactly what it is. It's probability density, but for now we'll just say it is the probability of something happening based on some combination of your age and how much money you make, right? And so the probability of it happening kind of corresponds to whatever this z value is here. And so in this class, it makes sense that if we could calculate the total probability in 2 dimensions, right? Back earlier we did it in 2D here. Well, now we're in 3 dimensions, and it's a very similar idea, except now if I consider, say, a range of ages, say from A to B in the X direction. I can also consider a range of incomes, say from C dollars to D dollars in the Y direction. And then the idea is that this region right here, this region that's lying down on the XY plane, right there, this region right here is basically our region of integration in 3D. And you can imagine that we can find the total probability by doing a very similar process to what we did in 2D calculus back when we were only dealing with functions with one variable. And, just to lift the curtain a little bit, it's going to involve doing two integrals this time, one of them going from A to B, and the other one doesn't take much brain power to kind of guess that the other one was going to go from C to D. And what are we adding up? Well, again, we're adding up the total probabilities, in the X direction and the Y direction. And so this is kind of loosely what we're going to be doing for a lot of the beginning of this class. And we can extend this to integrate over, not just 2D regions, because in Calculus 2, we integrate over one-dimensional regions, right? X just goes from A to B. That's a one-dimensional region of integration. And then we said, well, we can introduce a second variable for our probability calculation. We get a 2D region of integration, and we can, in theory, continue this for as many dimensions as we want, because, probability could be based on a whole bunch of variables. Maybe it's based on 3 variables. It's based on your age, your income, and how tall you are, something like that, right? And we could still, even though it becomes a lot harder to draw a picture, we can still guess that if we wanted to calculate the total probability, right? If we wanted to calculate the total probability based on all of those variables, probability, I guess I should finish writing that, we might, just add on another integral, and we would have different bounds, and we'd still be integrating our function. And yeah, we can't really draw it very well, but we could at the very least interpret what this means. And that in this class is going to be super important, okay? So I will write that down. It is supremely important. If you take away anything from this class, it is going to be super important, not necessarily that doing the calculations, like, okay, doing the calculations is cool and great, but a monkey could do the calculation. We have computers that can do it. ChatGPT can do these calculations. It is much more important that you understand the concepts, right? Understand the concepts, which, including what a mathematical expression means, right? Including what certain expressions mean, and kind of how to reason what they mean, and how to reason. Okay, because in this class, it is, I would say Calculus 4 is actually a very easy class to take, as long as you can draw pictures and as long as you can just talk out loud and say, oh, okay, well, if I want to add up all the probabilities based on one variable, 2 or 3, right? The concepts very naturally extend from stuff that we actually have already learned in prior calculus courses. So this is probably one of the largest concepts that we're going to start with in this class, is how do you integrate in 3D and higher dimensions. And then in the second part of this class, we are going to introduce vector fields, and we're going to talk about line integrals, and surface integrals. And these are kind of, they take a little bit of thinking, but, I will give you kind of just a rough intuitive understanding of where we're going with this. In the real world, let's say we're talking about the weather, right? You might imagine that if I were to draw a room, okay, and again, I'm going to stick to my X, Y, X, Y, Z axis. But you might imagine that if I was in a room, or maybe I was standing outside or something, and I was here in space, there might be some wind blowing in this direction. And maybe if I was over here, there'd be some wind blowing in this direction. And maybe if I'm here, there's only a little bit of wind and it's blowing in that direction. And if I'm here, there's a ton of wind and it's blowing in this direction, right? And this is essentially the notion of what a vector field is. A vector field, we will kind of talk about later. It kind of looks like a function, but it basically describes a scenario or a space where there are a whole bunch of vectors at every single point in the space. And they usually represent things like, so it could represent things like fluid flow, right? So fluid flow, like maybe if you drop a leaf in a river, right, what direction is it going to go? It could represent airflow, heat flow, could represent gravitational pull, so gravity, energy, a whole bunch of stuff. And you might notice that we're like, wow, all of those things are kind of pretty important. And yeah, they are very important. We use them everywhere for a lot of things, especially if you are going into a STEM field. So we introduce vector fields, and essentially what line and surface integrals are basically our ways of computing, doing integrals in 3 dimensions using vector fields. And so again, roughly, let's say, just as an example, let's pretend I have a light bulb. Okay, so this is going to be a terrible drawing of a light bulb, but there it is. There's my light bulb. A+. I'm a math major, not an art major. Okay, and so if this little vector field, this little space of arrows that I've drawn represents heat, right, represents maybe the direction that heat is flowing, it might make sense if my light bulb was turned on that heat might be radiating outwards from this object at this point, right? We would call this a source. And if I were to compute some sort of integral over this surface, so if I were to compute some sort of integral over this surface S, and I were to integrate the value of this vector field that's kind of maybe going, we'll say, normal to this surface. And again, you don't really have to understand exactly what this means yet, but the idea being that maybe we can think that what this would mean is it would kind of give us how much heat is radiating from this light bulb, right? You're adding up, how much heat is going normal. It's passing through the surface of this light bulb, which is a really good thing to know, right? If you're trying to figure out, if you're trying to build a computer and you're trying to figure out, do I need to put a cooler in here? It's a good idea to figure out how much heat is coming from certain spots, like a computer processor or anything else that's generating heat inside your PC build. And so that's very, very, very roughly just the 2 main concepts that we're going to cover this class. That will take us the entirety of this class, and we will go through all the applications of where we use all of them and all of that good stuff. So this was just a very brief, kind of very rough introduction as to where we are going in this class. And in the next video, we are going to get started with thinking about how to understand where integrating in 3D begins, which you may remember, just like in Calculus 2, we started off with Riemann sums, and those are going to come right back. So I will see you all in the next video.